Okay, chapter 4.2, we'll keep talking about how we describe the relationship between two quantitative variables. And in particular, we'll talk about the model, linear regression model. To talk about it, we'll stick with our example. Suppose we're interested in whether shoe size and height are related or not. So we can actually make slightly different questions. For example, are shoe size and height related? How are they related? Are they positively related or negatively related? So positively related means probably when a person is taller, for the taller person, the shoe sizes tend to be larger. If it is negative relationship, if a person gets taller, your shoe size is smaller. Can we make a mathematical or statistical model? Is the height a good variable to predict shoe size? So we can answer all of these questions by the end of the chapter 4. Okay, so here are some more broad idea. We can think about deterministic model or probability model. Deterministic model is we're assuming there's a exact relationship between variables. So what it means is if we actually draw a little figure here. So say here's your X variable, here's your Y variable, and somehow your data sets are exact relationship. So you can exactly predict one when you know X and Y will be just exactly on that line. On the other hand, the probability model is when you have an X variable and Y variable, you have a general tendency, well, this is probably general tendency, but your data points are not necessarily exactly on the line, but around the line. So in other words, you can describe the relationship between X and Y as there's a deterministic component. So there's some trend or deterministic component, and then there's also some random errors. Right? So it's not exactly on the line, but there are some random errors going on. So it's a probability model. Random error is unexpected variation. So what we're trying to do model here is not necessarily explain every single thing about this dots data, but we're more interested in the general trend. A probability model is more realistic. I mean, if you are getting a real data set, it's really rare that you're going to actually have a deterministic model, which is no error exists. But 99.9% of time, you will see from the real data, there are some unexpected variation built in your data set. So the probability model is probably more realistic. On the other hand, sometimes it is kind of hard to find what's exactly the best model, which means, two person might come up with slightly different lines. So, the blue person get this line, and what about red person think that, hey, this is the best line. So it's a kind of similar pattern, but it's a little different. And how can we find what's the best fitting model? Okay, so that's an added challenge, and we'll talk about how we can do that in a little bit. Okay, so once more, this is just a more graphical way of explaining things. We already kind of did that, but here, X1, Y1, X2, Y2, these are the combination of X variable and Y variable. So these dots are pretty much what this combination of those two values, X value, X, for example, this one could be X1 and Y1 value, X2, Y2 value, and blah, blah, blah. X is called typically explanatory variable. Y is response variable, we call that. Typically, we want to explain what's happening to Y using X. So another words for X and Y, we also called X as independent variable. and y is dependent variable. So typically, we'll want to say, we want to find that when x changes, how the y is depending on your independent variable x. Okay. Anyway, so what we're trying to do is, once more, find out that linear line, trend line, or deterministic component of the model. So this line is called simple linear regression model. And one of the main purpose of this chapter will be we figure out what this line is. Okay, so now it's time to think about some algebra that we learned in high school or middle school. So if it's x and y, and if it's a straight line, what is the general notation or general format that we use to describe this straight line? Didn't you use y is equal to mx plus b? Is that the notation that you use? Right, so we're going to actually use the exactly same thing. Here, if I remember correctly, the m is slope and the b is y-intercept. Okay, means m is the slope, which means when x increase by 1, what is happening to your y, right? So that's your slope. This particular case, no, it is actually upward trend. So when x increase by 1, your y is increasing this much, right? So that's actually what the slope is. The y-intercept is when x is equal to 0, what is y value? So pretty much that point, when x is equal to 0, what's the y? So that amount is probably y-intercept b. So we're going to do exactly the same thing. We're just using slightly fancier notation. So instead of m, we're going to use beta 1. And instead of b, we're going to use beta naught. And then we're just going to put the beta naught first. So y is equal to beta naught plus beta 1x. So that will be our model. And obviously, to explain every single data point, we also need to think about random error. Okay, so random error, which is, we call that epsilon. So we're going to use this model for our model, okay? Okay, once more. So here is our model. Y is equal to beta naught plus beta 1x plus epsilon, Greek letter epsilon. Here y is response variable or dependent variable. X is predictor variable or independent variable. Beta naught is y-intercept. Beta 1, slope. The beta naught and beta 1 are the ones that we probably want to know, right? To estimate it, using our data set. So beta naught, beta 1, in other words, those are actually population parameters. And based on our data set, we'll guess what those parameter is. And then epsilon is random error component. So once these are the parameter, and based on our data set, once we figure out what actual value is, beta naught and beta 1, we will call that as beta naught hat and beta 1 hat. So beta 1 hat is a guess of what beta 1. Beta naught hat is what the guess of the beta naught. And then your y also get hat because it's a guess of y value based on your beta naught hat value and beta 1 hat value. So for the fitted model, this is the notation we're going to use. Y hat is equal to beta naught hat plus beta 1 hat x. So anything, if you see the hat on, that's just guess of the under the hat. You can actually think that. Okay, so again, beta 1 hat is just guess of beta 1. Beta naught hat is guess of beta naught. Y hat is guess of y, or estimate of y. Okay, so that's our model. Once more, then you can see that that data set one more time. Here's a X, here's a Y, response variable, explanatory variable. Here's our fitted line. Y hat is equal to beta naught hat plus beta 1 hat X. So the question is how to estimate the slope and y-intercept. So how can we come up with this beta naught hat and beta 1 hat? So this part is a little bit more theoretical and mathematical and needs some calculus work involved. But I mean, we're not going to actually go through all the calculus because, you know, the prerequisite of this class actually is not calculus. So I'm going to kind of briefly explain what this number is coming from, but an actual calculation, we're not going to actually do it by hand, but we're going to use the StatCrunch. So the idea of least square method, so that's actually one of the popular way to find out what the slope and y-intercept is. It's based on this, for these things, so this is actual data set, and this is your guess, right? Y hat value for particular X value, right? So do you want, so the difference is called sometimes residual or error, or, you know, the guess of error is actually residual. But anyway, so let's call that residual. Okay, so these are all the residuals for the data set. And presumably, you want your data set to be explained well by the straight line. That means you want your line to be close to the dot. So in a way, you want beta naught hat, beta 1 hat value that has minimized these residuals, right? So diff is residual, right? Y minus Y hat. If it's the Y value, and if it's the Y hat value, so your residual is actually that. So you want this to be small. But again, there is an n of them. So if you add all of them, right, you want that thing to be small. Here's another catch. If you do these values for Y minus Y hat, it will be all positive values, right? Y minus Y hat. How about these values? This value, if you do Y minus Y hat, it will be actually negative values. These or anything that is down under the straight line will be negative value. So if you actually add all these values, it will be actually equal to 0, assuming that the line is actually going through in the middle of your data set. So instead of minimizing this thing, you wanna make sure that beta naught hat, beta 1 hat, that minimize the squared error. So that's why it is called least square method. So we want to find beta naught hat and beta 1 hat that minimize these errors. And again, the next step is actually involved calculus. We're going to skip that part, assuming that we use some the mathematical calculus way, take the derivative and all that, and do a little bit of math. The least square estimate for beta naught and beta 1, which we're going to call the beta naught hat and beta 1 hat, and these are least square estimate for beta naught and beta 1. And if you do that, the formula for beta naught hat is this guy, and the beta 1 hat is this guy. Okay, just notice that this is the correlation coefficient that we talked about in 4.1. And once more, later we're actually gonna revisit and the relationship between the correlation coefficient and other things. And here, before we actually forget, you kind of see that this R has a direct relationship with your slope, beta 1 hat. Okay. Just remember that. But anyway, this is the formula for beta naught hat and beta 1 hat, but we're not going to actually use this formula to calculate these values. I mean, you can definitely do it, but we're not going to actually do it. if you run StatCrunch or any other statistical package, it will automatically actually calculate this thing for you. And then we're going to actually take advantage of that. More importantly, we need to understand how to interpret these values, especially in terms of the relationship between X and Y, our independent variable and dependent variable. So how we're going to interpret beta naught hat and beta 1 hat. Once more, beta naught hat is a slope. Beta 1 hat is, beta naught hat is y-intercept, and beta 1 hat is slope. Once more, when X increases by 1 unit, what's happening to Y is actually beta 1 hat. So broadly, you can kind of imagine that the three different the graphs there. So remember when we're talking about R, this is a positive relationship. X and Y has a positive relationship going upward. So we say that if it will be actually larger than 0, positive value. This one, negative relationship, you're going to see negative value. And this one, you're going to see about equal to 0. Hold on a sec. About equal to 0. Somehow it doesn't work. Okay, so it has a similar thing. Y1 hat is the slope, and it's also telling us the relationship between X and Y. So this guy also, beta 1 hat, your slope is positive. This one, your slope is negative. And this guy, your slope is about to equal to 0. Okay, so you see the relationship between the beta 1 hat and then R. They are actually kind of, sharing the similar properties there. But again, so the way that we can actually explain using beta 1 hat value and R value, when beta 1 hat value is positive and R is positive, we can kind of guess the X and Y is positively related. When beta 1 hat is negative or R is negative, your coefficient is negative, you can say that they have negative relationship. If beta 1 hat and R is about 0, you can say that X and Y is not really related. If we go one more slide up, remember that if R and beta 1 hat, so it has actually one-to-one relationship there. These are all positive value. So in a way, when R is equal to, when R is positive, your beta 1 hat will be positive. When R is negative, it will be negative. If it is about 0, this one will be equal to 0. So you can see it from directly from the formula as well. Okay, now going back to our sample. So using shoe size example, shoe size and height example, we're going to write down our regression equation, explain their relationship using the slope, and then we're going to predict the mean shoe size for 65-inch person. So let's actually get the regression equation first. So once more, we're going to actually go to StatCrunch. Again, this is our survey data set. So if you go stat, there is an option called regression. We're talking about simple linear regression. So we're going to click simple linear there. And you just need to tell which one is X and which one is Y. And again, Y is typically depending on X. So I'm going to put the X as height and Y variable as shoe size. Okay. Sometimes it is not really clear which one goes X and which one goes Y, and it's just depending on how you want to answer it. So that's actually the minimum thing that you can do. I mean, there are other options too, but we're going to just start with the height and shoe size there, X and Y. So if you compute it, here is all kind of information available for you. Okay, so the couple things that you want to know, this is the beta naught hat and beta 1 hat intercept this upper one is beta naught hat. And the down one that is related to slope is beta 1 hat. Okay? And all the other ones here after your estimate, we're not going to actually worry about at this point. Later on, we'll probably talk about what's the statistics and the p-value and how we're going to make a decision based on that. But at this point, we're not going to worry about that. There are other places that you can also find your line, which is just right there. Right? So this is your equation, the linear equation. So in a way, I'm going to actually copy and paste it. Here, if you go back there, your equation will look like that. I guess it's a shoe size. Shoe size, which is, I mean, if you want to use y, you can actually use y there too. So this is shoe size, which is your y is equal to negative 10.1, negative 11-ish plus 0.3067 height, which is x. Okay, so you can actually say that. So that's your linear regression equation line. And then using that is asking, explain the relationship using the slope. So your slope is 0.3067. Let's call that. One thing, it is positive relationship. More in particular as the height increase by 1 unit, and it is actually inch, 1 inch. Shoe size also increases by 0.3067 on average. Okay, but if it's one way of doing that, okay, but something like that. So you can actually explain what's happening to shoe size and height using the slope is actually the whole point. And then predict the mean shoe size for 65-inch person. So how would you do that? Oh, by the way, this needs to be actually head, y head. So when a person's height is 65, so from your y head, negative 10.9021. Let me just do for this decimal point. And 0.3067. And then you plug 65, right? When you have a 65-inch person, and then you can just calculate what this value is, and that will be your guess of your mean shoe size. Okay, you can do that by hand, or I'm actually gonna cheat here a little bit. So what I'm gonna do is I'm gonna actually erase that, going back to regression, simple linear regression, and do one more time of height and shoe size, your x and y. And then if you go somewhere in the middle, there is the prediction of y component there. So I'm just going to put the 65 there, 65 inches there, and compute. And then what you're going to see is it adds this extra predict value component there. And this part is actually the answer of our equation. So 9 point, this value, I can go back and from, I erased the formula, but your y hat, okay, your y hat, y hat is equal to 9.033. So you will expect for the average 65-inch person will have a size 9 of shoes approximately. So that's how we can use this equation. Okay. We're going to do one more example in the same data set. This time we're interested in calorie intake and sleeping hour. So basically what I want to look at is, there's this either myth or theory that if you actually sleep a lot, you're gonna tend to have less calorie or something like that, right? So we'll see how it is working. So this time, I'm actually interested in the sleeping hour and how the calorie intake changes. So my sleeping hour will be X and my calorie intake will be Y, okay? And then I will draw a scatter plot. And then for this one, I just use slightly fancier word. So let's look at what I mean by that. So here, the second example, it says, what's the least square estimates for beta naught hat and beta naught and beta 1? This means least square estimate beta naught and beta 1 is beta naught hat and beta 1 hat. So what that means is, guess what the beta naught and beta 1 is. So what are those actual values? That's what that means. And then interpret the meaning of the least square estimate for beta 1. So this is your slope, right? So how you're going to use the slope value and interpret the relationship between calorie intake and sleeping hour. And then find the least square line, which means y hat is something plus something X thing, right? So that's your fitted line, least square line, linear regression line. Those are all the same words or same things, different words for the same thing. And then you predict calorie intake, who sleeps 6 hours. Okay, so when X is 6, what is Y? Okay, that's what this question is asking. Okay, so we'll need beta naught, beta. First, we're gonna draw scatter plot first. So let's go back to our StatCrunch. Okay, and I'm gonna close that. And then you go, I guess go graph first, graph, and scatter plot, and my X is sleeping hour, and Y is calorie intake. Okay, so if you compute, you're gonna see this scatter plot. So just looking at scatter plot, do we see any positive or negative relationship or no relationship? It's kind of hard to tell, right? Maybe a little bit positive, but it looks like, it's kind of random scatter a little bit. So we have a rough idea of the relationship between sleeping hour and calorie intake here. Okay. And I'm going to actually close that. And then go back to stat, and we're going to run linear regression, simple linear regression. Sleeping hour and Y is calorie intake. One more time. Okay, and since we've done this once before, I'm just going to put the prediction as well. So 6 hours of sleeping. You compute. And here are all the information there. And once more, this is your linear regression line, fitted line. So I'm going to actually go back there. And then I'm just going to write it down. Right? Calorie intake. Calorie per day is, but that's your y-intercept, and the 59 is your x-intercept, and then prediction. Again, this is the value, right? So, and I'm gonna just copy and paste there. I'm gonna have that. Okay, so I just copy and paste a whole bunch of them there. Okay. So I did draw scatter plot. So here you can say, let me do this. It's kind of moved. Okay. Anyway, so here you can say beta naught head is equal to 1680.274. And then beta 1 head is 59.1166, something like that. interpret the meaning of a least square estimate of eta 1 hat. So what is this 59.1166 means? Again, as our X was a sleeping hour, right? As a person sleeps 1 more hour, they tend to, he or she tends to eat 59.1166 more calories on average. Okay? In that line, you can actually say it. And everything else is done. Okay? So predict with somebody who sleeps about 6 hours, we predict that person will, on average, will take about 2,035 calories. Okay, but that's 4.2, and we'll come back in 4.3.